Yeah, so now I would basically start with some very fundamental math topics. So I'll start with very simple things that are used quite a lot. So does everyone know about GCD? All of you would have heard, right? So what is GCD of two numbers? So let's say the two numbers are like 6 and 14. Then how do you get the GCD? It says greatest common divisor. Okay, so this is important, common, and this is also very important, greatest. Okay, so if I list down all the divisors of 6, what are the divisors of 6? 1, 2, 3 and 6. What are the divisors of 14? 1, 2, 7 and 14. So there are many common divisors. This is a common divisor, this is a common divisor, these and these are not. Okay, so out of all the common divisors, whatsoever is the maximum one, okay, that would be called as the greatest common divisor. Okay, so this is the way you get GCD of two numbers. Now I have a question to ask. Let's say there are two numbers. You don't know what those two numbers are. Those are, let's say, just a comma b, and you are trying to compute the GCD of a comma b. Can you tell me what could be the maximum value of GCD of two numbers? Under any kind of circumstances, what could be the maximum value of GCD of two numbers? It would be min of a comma b, right? Can it? Yeah. So your GCD will always be smaller than or equals to minimum of the two numbers, because it can never happen that you have two numbers, let's say like 5 and 99, and the larger number that you have is GCD, because the larger number will definitely not be a factor of the other smaller number. Okay, but it can very well happen that if you have a situation like this, 15, which is minimum, is a GCD, which is in this case. So your GCD will always vary in between 1 to minimum of a comma b. GCD will always vary from 1 to minimum of the two numbers. So tell me, what is the easiest way to compute GCD of two numbers? I can simply write a for loop which starts from 1 to this thing. Okay, so I can have a for loop where I goes from 1 till min of a comma b I plus plus, and I will check if this I, since it has to be a common divisor, so it should divide both a and b. So if a mod I is also 0 and b mod I is also 0, then I can say that this I is a common divisor, but just a common divisor, not the greatest common divisor. Okay, not the greatest common divisor. So since I have to track the greatest common divisor, I can have a max variable which is initially, let's say, 0, and if this is true, then I can replace this maximum variable by max of this comma I. So this is the way you track all the numbers from 1 till min of a comma b, and whatever is the greatest number in between 1 to here, which divides both of them, that would be the greatest common divisor. Yeah, so how many of you think starting from backward is better? How many of you feel that instead of starting from 1 and going on till min of a comma b, why not start from min of a comma b and go until 1? That is better, because that way the first number which happens to divide both of them, that would be GCD, and you can immediately break the loop over there. Okay, so what is the time complexity of this approach? What would be the time complexity over here of this particular approach? It will be order of min of a comma b, right? Yeah, it will be order of min of a comma b. So this is not a great approach. There is a way in which you can compute GCDs in a way which is much faster than this. Do you all remember how you used to compute GCD in your high school? Yeah, so I'm just going to reiterate that. Let's say you are trying to find GCD of 7 and 25. So first you divided this by 7, so you got 7 3s are 21, and then if your remainder was 0, then whatever was your previous divisor, that was the GCD. That was the rule, isn't it? But if the remainder was non-zero, then what did you used to do? Then whatever was your previous divisor, that used to become the new dividend. Okay, and then you would perform the same thing that you did here would be done here again, that is, you divide it, and again you happen to see that the remainder is non-zero. So if the remainder is non-zero, the previous divisor would come and become the new dividend. Okay, and then again, okay, again this is non-zero, so again it will come down. At this point of time, you will see that the remainder is 0, so whatsoever was the previous divisor, that would be the actual GCD. Can you just tell me what will be the complexity of this approach? If the two numbers that are given to us are a comma b, can you tell the answer in terms of a comma b? What is n over here? I don't get. Neither there is an array of size n nor there is a number like n. I simply have two numbers a comma b. So can you tell the answer in terms of a b? So first see how we can get this done. So one way to get this done is by simply writing a while loop. You can have a while loop wherein you have two variables a and b. If you see that b modulus a is 0, then a is your answer, and if that is not the case, then whatever is b mod a, that is the new value of a, and whatever was previous a, that should be new b. So this is how you can get your job done using a while loop. There is a recursive way also to do that, and what is that recursive way? Recursive way is also simple. So let's say this is a GCD function that takes in int a comma int b. Okay, so although we will study recursion later, but to tell you a bit about it, what will you do? First you will determine that what is the maximum of both and what is the minimum of both, so that you can decide what is the dividend and what is the divisor. So I think you can get maximum by max of a comma b, and you can get minimum by min of a comma b. Okay, now what you can do is you can simply check if this maximum thing is completely divisible by minimum. If it is completely divisible, then you can simply return minimum as your answer. And if this is not the case, then you need to move on to the next iteration. When you move on to the next iteration, that is as good as calling GCD function for the new two variables. And the new two variables, first one will be remainder. So the remainder would be maximum mod minimum, and the new dividend will be the previous divisor, okay, which was the minimum thing. So this is the recursive way to implement it. Okay, now we will all try to understand the time complexity of this, and this is quite important, okay, because sometimes people tend to remember the time complexity of GCD algorithm. By the way, this is called as Euclidean algorithm. This is Euclidean GCD algorithm. So if you take a look over here, there is a very interesting thing to understand. That interesting thing is, let's say this is A and let's say this is B. I am going to ask you a simple question. That question is, can I say that whatever remainder I am going to get over here, okay, whatever remainder I am going to get over here, that will definitely always be smaller than b by 2, smaller than b by 2. Can I make this statement or not? So this is a bit tricky and I'll try to explain you, so focus your attention completely on the board. Okay, so let's forget about b completely. Okay, let's just think about a for a while. There can be two cases of a. First case of a is that this a thing is greater than b by 2. If this a is greater than b by 2, let us take an example. So let's say this was greater than b by 2, something like 13. Okay, then can you tell me what will be the remainder, what will be the quotient if this condition is true? If a happens to be greater than b by 2, what will be the quotient for sure? Can I say that my quotient for sure will be 1? Yeah, very good. So the quotient for sure will be 1. If the quotient for sure will be 1, whatever value comes over here, this value will be same as this value. Can I say that? It will be same as that value. Now when you perform the subtraction, now, whatever you will get, will that definitely be smaller than b by 2? Because this value is greater than b by 2. Now, second case, if my a is if my a is smaller than equals to b by 2. If my a is smaller than equals to b by 2, can I say that the relation between remainder and divisor is that remainder will always be smaller than divisor? So even in this case, what can I say? Even in this case, I can say that whatever remainder I'll get, that will be definitely smaller than a, which implies smaller than b by 2. So under both the conditions, I can say that whatever remainder I am going to get will be smaller than b by 2, and that is exactly what is happening over here. So what has happened over here is that let's say you have a and b. What will be the dividend? Can I say that dividend will always be max of a comma b? Can I say that? I think that is a common sense, right? Whatever is your dividend which you are dividing will always be max of a comma b. Now, the next number that you will get here, with which you have to perform the division, this next number that you get will for sure be something which is smaller than max of a comma b upon 2. Okay. Now again, the same thing happens at this level also, that whatever is the next value that you are getting will again be smaller than 7 by 2. Again here, the next thing that you are getting will always be smaller than 4 upon 2. So whatever next divisors you are going to get, see, your algorithm terminates when your divisor either becomes 1 or divisor completely divides the dividend. Okay, so every time what is happening, that the new divisor that you are getting is half of the previous one. So let's say the initial value was max of a comma b. So every new divisor that you will get will be upon 2 of this, then again upon 2 of this, which is 2 square, then again upon 2 of this, which is 2 cube, and so on and on and on and on. So what I am saying is that let's say the max of initial a comma b is being represented over here like this. So whatever your next divisor would be, that will definitely be smaller than max of a comma b by 2. Got this thing right? Now this thing happens at each level, because now let's say you got a value over here. So now again, whatever will be the new divisor at next level, that would be smaller than max of this and this. And max of this and this will definitely be smaller than max of this and this. So again, I can say that whatever value I will get, that will strictly be smaller than max of this upon 2. At the next level, it will be smaller than max of this entire thing upon 2, which is 2 square. At the next level, max of this thing upon 2, which is 2 cube, and so on and on and on. So eventually what will happen, that in the worst case, this will keep running till my divisor becomes 1. So let's say I say that in the ith iteration, this thing becomes 1. So 2 raised to power I will be max of a comma b. So what will be the number of iterations? Log of max a comma b to the base 2. This is quite important concept to understand, that how the complexity is logarithmic for this Euclidean algorithm. And there are many other questions which are simply based out of this thing, and knowing this helps that the complexity will be logarithmic and not anything else.